Augie, Kathryn, and Chili each wrote a cubic function with the zeros 3, 1, and -4. And we showed that basically all of the oranges are the same. They produce a x-intercept at 3. And then we also showed that setting those equal to 0, fancy word is zero product rule, is that all of the x minus 1s turn into x equals 1, the pinks. And then we also had the yellows, those turn into -4. So, the leading coefficient you should have recognized is out here. Class, is there a positive or negative number here?
Positive.
Positive. So Augie's is positive. How about Kathryn? Positive, and Chili's is positive. How about its degree? Well, we kind of did this before. If this is x to the first, x to the first, and x to the first, and we've been doing this for the past week, x to the first is what type of function family? It's linear. 3 linears are equals a what? Cubic, you guys said. So is this even or odd? Odd. Does that mean they're all odd? Yeah.
That was odd too.
Okay. Partner A, I want you to explain what the leading coefficient will do to our graph. And then partner B, explain what an odd degree polynomial will do for our graph. Take 30 seconds. Ready, set, go. Elissa, what is an easiest odd degree polynomial you know? Shh. What does that mean, Elissa? Easiest one she knows is x to the first. What do the arrows look like? A straight line. So what are the arrows like when you draw a graph? Okay, it's a straight line. So here are the arrows. You're starting where? Up or down? Down, and you end what? Up. Starts down, ends up. Marco, do you know what the leading coefficient does to our graph? Do you know what the leading coefficient of a positive does to our graph? Everyone talk to your partner, 5 seconds. Yes. Marco? Okay, so we already know it's positive, so what does that do to the graph? Question, do the arrows switch? Are they flipped over the pen? Yeah. A positive leading coefficient says you're not going to switch the arrows. If this was negative, what would it do? It switches the arrows across the x-axis. Okay? Okay. Now, think of a vocabulary word in your head for the power of 1. Whisper it to your partner. I'm kind of pointing right here. This is what I'm really pointing at. On the count of 3. Ready? 1, 2, 3. Okay, it is an exponent, but we've been talking about a word. Everyone say multiplicity. The multiplicity, is it odd or even? So it's going to shoot through. Let's go ahead and try to sketch this. I'm going to start here, go left to right. We're going to shoot through the yellow, shoot through the pink, and then shoot through the orange to end up here. Class, what type of graph do we have here? Odd, but it is a... These are cubic graphs. Cubic. Let's try it again. Where do we start? Start over here. Which direction am I going towards now? To the right. What do I do at this yellow one? Shoot through, because it has a odd degree. What do I do at the pink? Shoot through. And what do I do at the orange? Shoot through. Okay? Do it again. Class, which arrow do I start at? Bottom one. Because it has a multiplicity that's odd. Shoot through it. Shoot through the pink. Shoot through the orange. And now you've made a cubic function. Take 20 seconds, clarify any questions your partner has so far. So how does multiplying by a constant affect the graph of a function? A constant is the number in front. So my example is 1, 6, and 1, 6. So this is a parent function. And if you multiply it, you might have more energy, so it might stretch it vertically or compress it. The 0 stays, so that red dot stays the same. It doesn't move. Why does the zeros remain the same after multiplying it by a constant? Multiplying 0 by a constant still results in the same 0. How many different cubic functions can you write for a given set of zeros? I can write an infinite amount of functions by multiplying by a constant because it does not change the 0. So my example to that is the previous problem that we just did. The students, Augie, Kathryn, and Chili all have different binomials. But when we graphed it, we recognize that Augie's graph, Kathryn's graph, and Chili's graph, some of them have a higher maximum or a lower minimum. But essentially the big idea is that where it crosses the x-axis doesn't change.